excellent turnout. We are on the water kick because we're lucky enough to have Dr. Christina Buck here talking about the surface water, groundwater interaction. But we also have next week, to plug that, a week from today, we have Dr. Jean Moran from Cal State University East Bay, who's going to talk about her isotopic studies in looking at the recharge for the Tuscan aquifer. So we are on the water kick, so please tell your friends, come back. This is a very pertinent issue. Obviously, it was and will be for a while. So Dr. Buck is actually a local, at least where she got her PhD, is UC Davis. And I asked her, since I've seen, she now works for the county, as most of you know, but I asked Christina, can we have a science talk, please? Can we have a science talk? Because we haven't had one here yet in this seminar. And I said, you have to reach back to your PhD research. And she said, absolutely. She had to dust off some things, and because she defended what, a year ago? 2.5 years ago. So she'll be talking about managing groundwater for environmental stream temperature. So thank you, Dr. Buck.
Thank you for having me. It's fun to be here. I had to kind of pull this out and refresh my memory a little bit. And so dissertations are fun. They take a lot of work. Kind of shows like this. It's double-sided. But if you're inclined toward the studious side and like the academic world, it's a lot of fun to kind of continue in school and do some interesting research that has some flexibility kind of in what paths you can go down as new questions pop up, and it never ends quite the way you think it's going to end when you start. So I'm going to frame this kind of in light of that, of what we can learn from different modeling approaches. And so this work is done up in the Shasta Valley. It's Mount Shasta. Beautiful, beautiful country. This is Big Springs Creek coming down from, just originates as springs and flows into the Shasta River. And so it's a pretty awesome place to do field work. Tromped around out there a little bit and then spent most of the rest of the time, of course, on my computer, crunching numbers and writing. So it's always fun to have pictures that remind me of the fieldwork part. So today, there were kind of 3 related but unique parts to my dissertation. I'm just going to focus on 2 of them today just for time. And kind of in the context of describing 2 different modeling approaches that helped us integrate and expand knowledge about a system, in this case, the Shasta Valley system, and related to stream river flow temperature, as well as groundwater flow and temperature. So the first part will be groundwater modeling and how that helped kind of understand and test our understanding of the groundwater system in this area. The second will be optimization modeling and looking at stream temperature benefits. And then the third part, which I'm not really going to talk about, but was fieldwork component with data collection of stream temperatures using distributed temperature sensing technology, which is basically fiber optic cable that allows you to measure temperature every meter for as long as a kilometer. So we put this kilometer long fiber optic plastic bound cable in the river and then got this like massive pile of data out of it. And so that was an interesting kind of technology to use. It has a lot of applications for atmospheric science, hydrology, all kinds of stuff. They're using it in soil temperatures. So just a little plug for that. If that piques your interest, C-Temps is at the University of Oregon, I believe, and I worked with University of Nevada, Reno, and they have this kind of center that allows young researchers to borrow their equipment, at least at that time, applied, and got access to the equipment, support for them to support some of this research. So that's all you're going to get on that, but it's a little aside. So the motivation for this research really was acknowledging that groundwater and surface water are connected. We know that as scientists, as geologists and hydrologists, but the state of California, until about a year ago, in water law, didn't. We had a separate groundwater law system from our surface water law system. And so coming at this from that starting point really was to say, we know that groundwater is often important for flow in many systems, for base flow, right? It can be a major portion of the flow in the river, but it can also be really important for the temperature side. Up in Shasta Valley, there's major springs that are an important cold water source during the summer when the rest of the system is heated up. And they're actually an important warm water source relative to everything else that's cooled down in the winter, and provides opportunities for aquatic species, plant growth, bugs that the fish love, and things that wouldn't normally grow and thrive in the winter months because of this warm water source. So it's important for flow and temperature, and so that has potential benefit for ecosystem health and restoration, i.e. This is really motivated in this case by fish, mostly coho, chinook, migrating salmon species, as well as the more traditional water supply motivation, right? So trying to integrate both of those, so surface water and groundwater with flow and temperature for environment and water supply. That's what we do in water, right? We do all these different things. And it's really fun, it's really challenging, and it's kind of impossible, but we gotta move forward, right? So this takes just a little bite into some of those problems. So the case study is the Shasta River. The problem there is one of low flows and and high temperature. It's too hot in some parts of the river for migrating fish and for spawning. And so the approach to my work was really to first contribute to the understanding of the groundwater system, and then explore coordinated management of surface water and groundwater resource to help benefit stream temperature. As it turned out, those ended up being kind of independent, separate, but related topics, kind of folded into this one idea. So the motivation here, specifically, is the Shasta River was historically one of the most productive salmon streams in California. Over 80,000 returning salmon in the 1930s. That number is drastically reduced. In the 90s, it was in the hundreds. I think it's a little better than that now. There are chinook, coho, and steelhead that come back to the Shasta River. And it's been identified by the Department of Fish and Wildlife as one of the most important spawning nursery areas for chinook salmon in the upper Klamath Basin. So there's a lot of interest because of those reasons. So here we are. This is the Klamath Basin. Klamath River flows from Oregon out to the ocean. There are a number of dams on the Klamath. The Shasta River is the last tributary before the first dam on the river. So it continues to be an important tributary for salmon because of that. Scott River, you may also have heard about in the news, a lot going on there in terms of groundwater, surface water, and fish as well. So here's the Shasta River. It has one dam on it, Winnell Dam, which backs up Lake Shastina, and you'll see that in some other slides. So groundwater dynamics, the objective here was just to be able to reasonably simulate regional groundwater flow and be able to kind of explore relationships between recharge, spring flow, and pumping. And so the idea of saying, let's do groundwater modeling becomes what data do we have to quantify those, and it helps us organize and clarify our conceptual model of how the system works. So in doing that, it provides a valuable framework too, to have conversations about what we know and what we don't know, and to try to fill some of those data gaps and what our assumptions are. So hopefully that all advances our understanding of how the system works and what the groundwater dynamics are. So the Shasta Valley geology is super interesting and super complex. I focused on the Pluto's Cave basalt area. This is a volcanic basalt flow that is, there's actually some discrepancy in the literature as to where it originated from, whether it's from kind of the Mount Shasta area or the Whaleback Deer Mountain area. So there's a couple different variations of geology maps. That's the first fun unknown about how are we going to conceptualize how the system works. And then the other interesting volcanic debris flow is older than the basalt flow, and it's chaotic. It was from a debris avalanche from Mount Shasta, much like what we saw when Mount St. Helens exploded and deposited this chaotic debris flow. And so it's understood to be a bit of a barrier to groundwater flow. So you have this highly productive basalt aquifer. It's not your typical alluvial sand gravel system, right? It's fractured rock. It's described, here's this great quote that says, groundwater is transmitted along the vesicular contacts between flow layers. So you had a basalt flow and then it cooled, then you had another basalt flow, but that was such a crinkly, uneven system that now you have space that water can flow in between these flows. Through joints and fractures within the flow, and through open and collapsed lava tubes where these occur below the water table. So this is not kind of your normal system that you typically model, right? But on a large regional scale, you can say, all right, we know groundwater isn't moving through this kind of consistently like we would model a river system, alluvial valley. But on a large system, there's large fractures that are interconnected, and so we're going to use that kind of general model to describe and try to model this system as well. And so that was the challenge. There is no, before this, groundwater model in this area in the Shasta Valley at all. Probably they knew better not to try this, but it helps. Like I said, again, we're not trying to, you geologists are probably dying a little bit inside, right? Like, you're going to simplify this down to this coarse 1K factor that's going to describe this crazy Pluto-scale basalt aquifer. Yes, we are.
It's just basalt.
It's just basalt. Anyway, if you haven't gone hiking up in Lassen area or seen lava tubes, they're pretty cool. So there's a good plug. You can just put your headlamp on and go check it out. So Big Springs Complex is that first picture I showed you. This spring complex results in that river, basically, that you saw in the first intro slide. So it's about 60 CFS during the irrigation season and up to 85 CFS during the non-irrigation season. Why the difference? Well, there's some high pumping production wells that are close by that apparently directly influence the flow of this spring system. So essentially there's like no water, and then all of a sudden there is water, right? There's a series of springs here. It's backed up with a little dam here so that some of it can be diverted for ag from that diversion point, and then it continues down. There's another called the Alcove Springs, another spring complex right here, and then it continues down, and this becomes important inflow, like I mentioned, for both flow and temperature to the Shasta River. So you can see it just bubbling up. So it's a pretty unique area. So to put together the groundwater system, the groundwater model, you have to identify what are the moving parts here, right? What are the inputs that we need to estimate? There's ag land up there, mostly, well, I'll show you a couple pictures. Ag land, so some of it's dependent on groundwater pumping. There are a couple of major canals that come through this area, and they are leaky, and there's been a couple studies on that, estimating that. There's recharge of precipitation that occurs in the valley area on that ag land and applied water that's going to recharge into the groundwater system. There's Mount Shasta recharge, and then there's these boundaries that we have to make some kind of assumption about, right? What's happening up here on the north? Is this a no-flow boundary, and generally the groundwater is moving from east to west, or something different happening there? The east side, originally, I assumed it's pretty typical to say east side, no flow boundary, and we'll kind of go from there. So initially made some assumptions about, okay, what are the parameters and how are we going to set up this system? And then other boundary conditions like Lake Shastina, that was modeled as a constant head. Springs, I wanted to include those directly in the model and use those as a calibration target to say, I have an estimate of what the spring flow should be from these different places. Can we get the groundwater model to simulate that? So we used the drain package. This was a mod flow groundwater model, just steady state for 2008, to see if we could kind of make things add up and make sense. So Mount Shasta recharge, I'm just going to focus on a couple of those inputs and not go into all of them, but this was considered to be the main recharge source of the Pluto-scale basalt aquifer area. And so said, okay, let's try to estimate what that recharge might be. So the interesting thing about the north side of Mount Shasta, if you've ever driven north to Oregon, you've driven right through the Shasta Valley. So I-5, you go through Weed, up over the hill, and drop down into this valley. That's the Shasta Valley. And so the north side of Mount Shasta has essentially no surface water drainage off of it. They have there's a few ephemeral streams, Whitney Creek and some others, but all that water, snowfall, rainfall, it either goes one of three places. It evapotranspirates by the native vegetation that's there. It sublimates straight from snow to evaporation, right? Or it recharges and disappears into the groundwater system. So that was the basis for estimating that recharge portion. Let's estimate the precipitation using PRISM data, which is spatially distributed estimations of precipitation. EcoWatt, which was an ecosystem water program, to estimate the ecosystem ET, the native vegetation ET. That alone is kind of an interesting bite out of how do you estimate native vegetation water use. And so this little EcoWatt is a spreadsheet model, essentially much like an irrigation demand calculator that essentially takes atmospheric conditions and information about soil and the plant, and then calculates or estimates water use by that vegetation. And then search the literature basically for a number that might be reasonable for sublimation. And so 30% was used for loss of precipitation. So here's a picture of land and water use in the valley. The green areas are groundwater dependent, and I just kind of numbered them for different ag zones. This is what the landscape looks like. The native vegetation in the valley floor is mostly conifers and sagebrush. And then the irrigated areas, mostly flood, irrigated pasture, alfalfa, grain, and then some other minor crops. So that's mostly what you're looking at for land use. Mostly surface waters. The blue is used along the creeks. There's Parks Creek over here that joins. This is Lake Shasta, Shasta River, flows north out to the Klamath, which was up here. And this is Big Springs complex that we talked about, and creek. So again, then representing the hydrogeology, right? So starting with the geology map, and translating that into basically hydraulic connectivity zones. The thickness of the aquifer varies quite a bit. So the Pluto basalt is much, much thicker up here in its origin areas, and then it thins and pinches out somewhere in here, and it's highly variable in those areas. And so to compensate for that, there's zones, the K zones are broken up across this landscape because of that. So that transmissivity, right, which is thickness times hydraulic conductivity, can be kind of consistent as you move through. So once you have all your data input, figured out kind of how you're going to try to represent the K hydrogeology side of things, now you're going to run it, get results, and you have to compare it to actual data, right, to see if it's any good. So we've got groundwater elevation targets. Here's another bit of unknowns. There's not a lot of groundwater monitoring wells up there. We had about, I think, 4 or so to work with within my model domain. So again, you have to get kind of creative and say, all right, what other types of information are out there that might give me some information about groundwater levels. In this area, you can see I didn't have any originally, but you can't really tell. But here is one. The blue under the cross mark is the monitoring well, so there was really only a couple over here. So I pulled out well logs. When a new well is drilled, the well driller is supposed to submit a well log to the state of California. These vary wildly in terms of the quality of data that you're going to find in them, but they describe the type of material that they encountered as they drilled, and then also maybe they'll record where the groundwater level was when they drilled. So I basically used that to fill in a couple points, still pretty sparse, but it gave me something to go off of for some of these other areas. So I've got a handful of elevation targets, and then like I mentioned, I want to try to represent spring flow in a reasonable way. And so these became calibration targets as well. There's some spring-fed lakes in the north, the major spring complex that I talked about, Big Springs Creek, and the lake there. There's a few other major ones that are on the order, I think like 4 to 6 CFS. So still a significant amount of water from hole in the ground, clear spring. Lake Shasta is also known to be really leaky, and so when they built Dwinell Dam and flooded the lake, some of these springs on this side of this is a debris flow material forming the side wall of the lake, either increased in flow or started flowing. So even though the debris flow material is relative to the basalt, low conductivity, and so at that contact we get these springs. Some of these other springs are understood to be at that contact. We also know that water is still moving through the debris flow material, and to what degree is kind of unknown, but it's leading to some springs on the backside of this ridge there. And so I had some estimates of those spring flows as well, and so could try to use that to calibrate my lake leakage. So I'm not going to dig too much into the details in terms of detailed results, but I want to talk about kind of the process of once this was up and running and I was playing with, okay, what are the results? What do they look like? What's affecting what, right? So if I basically discovered that there's this connection between flow that's coming from the north and western boundary. So this is the northern boundary and the western boundary. What's happening with groundwater flow in those areas, depending on how I turn the knob of conductance along those boundaries, had an influence on the spring flow from Big Springs Creek down here. And so I said, I don't have a lot of good information on that northern boundary or on the western boundary, really. So let's make some different assumptions. Let's create 3 different scenarios and test those, because I don't really know, I don't have enough information to know how it should be to start out with, maybe. So with that, sometimes you have these big unknowns and you have to kind of play with different scenarios to explore those. So again, I calibrated basically 3 different, a high, a moderate, and a low scenario, saying that let's assume there's no flow coming from, essentially no flow coming from the north. What combination of K values is needed to make reasonable head and spring flow occur? And then what if there's kind of moderate flow across the northern boundary, and then a little bit in this northern tip also? What calibration combination does that look like? And then what if I allow a bunch? This is high conductance, there's a lot of flow somehow coming from that north side. So using that uncertainty, you can kind of create these different scenarios and then play with those. And so with those 3 different concepts, really different concepts of how the system's working, I then played with sensitivity of ag, groundwater pumping, recharge of Mount Shasta, and local recharge, which included canal leakage and precipitation on the valley floor. So to try to explore kind of what the relationship was between recharge and pumping, essentially. So that was the process. Kind of felt like I had to show you this, right? You want to compare your targets to your model results, and you want it to land on the 1-to-1 line. It mostly did. You always have a couple bad behaviors over there, and sometimes you say what's going on there, and you can kind of drill down and fix it. And sometimes you say somehow I'm representing the structure of the system incorrectly, probably, but I'm not sure how that is. So you can kind of go back to your scenarios and tweak things and try to explore what's going on in these different places. So as a result, you also get a mass balance, right? You don't have to do a groundwater model to do a water balance on a system, right? You can estimate the inflows and the outflows without a groundwater model. But a mass balance is really helpful then to be able to go to people who are familiar with the system and say, what do you think? Like I've quantified all these different inputs and outputs. It looks like Mount Shasta recharge is a big portion of the input, 61 million cubic meters, compared to lake or canal leakage is on the order of 7, local precip and applied water is 21, ag pumping's on the same order of magnitude, about 23, spring flows are major outflow from the system, about 83, and then lake leakage and other components of the system. So you can kind of see in relation to each other what are the major parts and what really matters. Maybe what we thought was important is actually a tiny little bit of the system, and we don't need to spend a lot of resources to get better data to refine that. We really should spend our time figuring out what the heck is this number, because it's a really important part and major inflow to the system.
So which conditions do you use to get your mass balance based on your 3 scenarios?
The moderate. Yeah, good question. So I basically took those 3 scenarios to a group of folks that have done a lot of work in this area, mix of biologists, hydrology, water resource engineers, and that's kind of scary, right? You put all this stuff together and then you go, what do you guys think? Does this make sense? And really helpful conversations come out of that, right? They go, yeah, there's no way that much water can be coming from the north. So it's got to be coming from somewhere else. Where else could it be coming from? We originally assumed that this was a no-flow boundary. What if it's not? So go back, do some more number crunching, estimate what the precipitation is in that area, estimate what the ET of vegetation is in that area. There's probably less snow there, so maybe you don't have to worry about sublimation, and come back and see where else could this water be coming from. they also said, this is kind of a refined mass balance already, but they also looked at my original mass balance and said, your recharge from Mount Shasta looks a little low. We think it's probably bigger than that. So is that possible? You know, what could be leading to that? So go back and kind of reassess. I originally kind of looked at a piece of the pie that came straight out back from this. What if there's recharge from over here coming in? Is there potential for additional flow from some of these different areas? So I think that's one of the lessons learned take home, is that when you go and you crunch all these numbers and then you bring something back, it really gives you something definitive to talk to people about and say, what were our assumptions and our understanding of this system? And does that jive with the other expert knowledge that's out there? And if it doesn't, how can we adjust and explore how it might be different from how it was originally framed? So, like I said, kind of revisited the conceptual model, went back and estimated recharge from these other areas, and that's actually what led to, with the moderate and a slightly recalibrated, ultimately started with the moderate scenario, recalibrated a little bit, and then came up with this mass balance. So there's a lot more to do on the mass balance, on the water balance, and on the groundwater model for the Shasta Valley. It's really just beginning steps of trying to integrate a lot of different sources of information. Almost any part of those inputs could benefit from additional data. I mean, that's always pretty much almost always true, right? Canal leakage alone, you could take that piece and help fill in some of the holes there. But nonetheless, doing a project like this in any system helps you identify, describe, and quantify your major flow paths and try to understand which ones matter, what's the relative relationship between them, and to be able to start to play with how they interact with each other. It gives you a framework to talk to people, to get feedback, and incorporate, again, kind of the expert knowledge that you may have missed or want to include. Again, data gaps, which ones really matter to help you for the next guy, right? Like, I'm moving on, I gotta like wrap this thing up and tackle the next project, but there's more work, and there's a lot of folks up there that are still living with a lot of these questions, and so hopefully giving them some recommendations from this work in terms of what data would be valuable going from here. And then knowing the limitations of the model and being explicit about that. And part of that in this area, it's highly political. There's really important water supply demands up there, and then there's this fish needs, and there's a big struggle between the two. And so being explicit and saying this groundwater model right now as it is not in a position to make management conclusions or resulting policy decisions. It's really just a test tool at this point to try to refine our understanding of these flow paths and things. So that's that first kind of groundwater modeling as an approach to kind of begin to explore and understand and hopefully expand our knowledge of the system. So part 2 is optimization. Optimization asks the question, what's best? Given a number of decisions that I can make and an objective that I have, like stream temperature at a certain point, how can I make the best combination of decisions to meet that objective? That's basically what optimization does in math form, right? So in this case, it's used to use basically different water sources. We've got groundwater, we've got surface water. They have different flows that are available, different temperatures, and how can we use them to meet a temperature objective? So I'll describe that a little bit more. It allows you to explore trade-offs. So if you want more of one thing, what do you have to give up to get that? And what's the relationship between those things? And kind of spoiler alert, one of the conclusions from this is that timing matters. It matters when and how you distribute your, say, reservoir releases and your diversions, and that can make a difference in stream temperatures. And so how you manage your system matters as far as timing goes. So I'll give you the background to that. So here's another part of the Shasta Valley. This is the Shasta River right here. Basically, this is the little corner of Lake Shastina. So you saw that in other maps. And then there's reservoir releases from it. It goes into the Shasta River. This part of the Shasta River is very low flow. It can be like 5 to 20 CFS probably. So because of that low flow, it heats up quite a bit, which is why that Big Springs Creek input is so important. That's like 60 CFS that comes and suddenly makes the Shasta River a significant river again. Nevertheless, there are some places in here, Parks Creek enters right here, there are some places in here that could be potentially good salmon spawning and over summering habitat if they had certain temperature characteristics and certain flow characteristics. So that's the idea is, can we manage kind of these different sources with that in mind? So to simplify the system, there's basically, we're going to describe the river as a series of nodes, right? And so we have input from the dam that has a certain flow and a certain temperature. There's a well right here that currently serves ag right here in this area. Okay, here's where the crazy idea comes in. You say, all right, groundwater in this area has a pretty constant, typically low temperature compared to the river water. So could we use that well as a managed cold water source? Instead of pumping it onto the field and using it in the field, what if we used hot surface water from the river on the field and pumped the groundwater into the river as a cold water source? Okay, this has all kinds of political and environmental things that would have to be dealt with, right? But from would it even matter? Like, would you even want to go down that road? Let's see if you could use that as a managed cold water source. You could also pretend that this is a spring and manage it and say, we're going to manage this spring. It's a cold water source. So there you go, it's a well. So then you go downstream, there's heating that occurs from point A to point B, right? So we have to account for that. There's a couple diversions here and here for ag that's along the river. And then what happens is that water is diverted, put on the field, flood irrigated, and then it comes back into the river at some place, but it's heated up on that field, and it's coming back into the river really hot. So that's a hot water source that is basically damaging our ability to hit our objective. And so our objective is to have a certain flow and a temperature target, in this case 18 degrees, which, talk to my fish friends, I'm not a fish person. So, and they said, yeah, you know, if you could get it 18 degrees as a maximum, I think maximum, or maybe an average daily, the fish could probably do okay. So, okay, we'll plug that in and use that as an objective for temperature. So that's kind of the system. The objective then is to optimize the use of groundwater from that well as a cold water source, the timing of diversions when you're going to pull water out of the river, and reservoir operations when you're going to release water from Dwinelle to minimize river temperature at that downstream location. So you can do this by making decisions about, like I just said, reservoir releases, diversions, and pumping. Both volume and timing of those, right? Given what you know about temperatures of each of those different components and relationships between them. So in math, this basically looks like I'm going to minimize, there's a cost associated with pumping that groundwater. I want to minimize that and account for it. There's a shortage cost associated with not diverting water, right? If farmer A wants 100 units and he only gets 50 and can only plant half his crop, there's a cost associated with that. So that's our shortage cost of him not getting the water that he normally would or wants to produce his crop. And then the temperature component. So this is driving meeting that temperature objective at the bottom of the reach. And we can scale that, the importance of that, by this alpha factor. So if that's super, super important, I hit that with a really big number and make that a bigger part of my objective function. And then temperature target of 18 degrees.
What is min z?
What's it? So I want to minimize z, and z is used as kind of the objective function value. That's kind of typical optimization, but it doesn't really have any application.
Yeah.
So this was just a spreadsheet, Excel-based model that simplified this river system into these 6 nodes and made things multiply out and add up. And so it used, however, a more complicated stream temperature model already existed, and so I used that to give me information about how water heats up as it moves from point A to point B to point C through the river. And so this was an hourly model for a week in July. Basically super hot temperatures, long days in July, so if we can make it work for a week in July, we can learn something for that for the rest of the year. So it's subject to all kinds of things. Conservation of mass, of course, right? The water flowing into a node has to equal the water flowing out. of the node or the change in storage. Minimum in-stream flow requirements at different points in the river. Water supply constraints, so we want to deliver certain amounts of water to the ag demands. Return flow constraints, capacity constraints in terms of how much you can pump, release, things like that. Temperature constraint, and then heat balance, right? Your heat into a node has to equal the heat out of a node. So results, here's a little picture from kind of a toy model, but gives you an idea of how timing matters. So if you have kind of 100% of your inflow, this is the optimization results. It says, okay, I see that you want to do all this stuff to hit this 18-degree temperature target. Here's how I can make it happen for you. So it's going to pump groundwater. This is midnight. It's going to pump groundwater and release a little bit of water from the reservoir, but it's going to mostly give you this hot return flow because it's the middle of the night and these other sources are cold. Then when the reservoir is the coldest temperature, right, because the reservoir water is coolest in the early morning hours, heats up during the day, and then cools down again the next night. So when that input of water is at its best in terms of temperature, it's going to release as much as it can, right? It's hitting a constraint here, well, here, I guess, to meet flow requirements. And then as it warms up, it's going to decrease that amount of reservoir release. It's going to pump your cold water source to its maximum capacity, and then introduce your hot return flow when you've got kind of these cooler sources available to balance it out. So for the Shasta River, at least in this initial look, it can make a significant difference kind of if you played with the timing and the source of these different things. So originally kind of under current operation, so there's no groundwater pumping going into the river, there's typical diversions and releases from Dwinell, you get this kind of temperature signature, typically from about 20 degrees Celsius to 24 to 25 degrees peaking out each day. This is not good for fish, right, which is why they're not there, typically. But if we rearrange and optimize how the system goes, we can get this darker fat gray line down here, which we're maintaining our 18, I think it actually had to be bumped up to 18.1. 18.1 degree temperature target and minimums of 13 degrees. So it's like, oh, wow, you could actually make a difference in the temperature signature of the river. Yeah.
Here, the bottom curves there
Yeah.
has like the bench before it's hottest, and or on the ones on the right.
The bench,
Yeah.
like here.
Lower, like you see before it gets to 18, like more towards the 4th and 5th.
Like these.
Yeah, those benches, like those benches.
Okay.
It seems like those are the same on your previous slide. You're not just having your cold water in. It's like first ramps up a little bit and then it changes the rate and goes up on your previous slide. I'm wondering why, like where does that tiny little curve come at like 8 o'clock?
Like here?
Yeah.
Oh. Yeah.
The cold water. Like why?
This one, why it drops off right there?
Yeah, exactly. Why does that happen? Why would you do that?
That's a good question. Let's see if so this is kind of from a toy model with just one point. Let's see if that shows up here. This is the result of the Shasta River study application. So Shasta releases, yeah, it has kind of this double spike in releases. I'm not sure. It might have something to do with the diversions. So the diversions also spike. Maybe those times come.
Yeah, I just thought if it's not too hot, then you don't need to start adding cold water. But it seemed like you wanted it to plateau before it got to those 18 degrees. That's when I cleared the story there, but.
Yeah, I'm not sure. Yeah. But those are good questions that you could dig into and be like, what is going on here? Yeah.
Christina,
Yeah.
how is the temperature propagation being modeled, right?
That's a good question. And actually, so I kind of stripped it out, but it is a regression. Well, I'll just describe it. So what we did is we took that stream temperature model and used that to run a regression based on solar radiation, daily temperature, and flow. So now the heating basically from point A to point B is a function of physical condition, atmospheric conditions, but also flow. And that flow is our decision variable. So as that changes based on the optimization decision making, it changes the rate of heating at each stretch. Does that answer your question? So by simplifying it down to a regression linear equation like that, allowed us to incorporate it into a simple spreadsheet optimization, linear optimization model. And so then just to point out, looking at trade-off curves, this is what I mentioned, the alpha allows you to basically communicate your importance of the temperature component. And so if it's really important to meet that average temperature, we're going to bring it down below. The average temperature is going to be lower than the 18 maximum. That comes at a high storage cost. Because basically what's happening is that it knows that, okay, if I divert this amount of water, there's really low irrigation efficiency on these flooded fields. And so a bunch of that water is going to come back into my system, but it's going to come back in really hot. So I don't want that. That makes it hard for me to meet either my objective of 18 degrees or it brings up my average temperature. And so I'm just not going to deliver water because I know it's going to punish me up here with hot water. So it comes at this really high cost of not diverting water. If you're okay with a little bit higher average temperature, then you can bring down the shortage cost quite a bit, from 7,000, from 15,000 down to 7,000. It's still high, you're still not delivering quite a bit of water. So that really results in this conclusion that this irrigation efficiency is an important knob that's going on. And the more you can crank down that input of hot water coming off the field, the more the model will say, okay, it's not so bad to divert water to the field if I know it's not going to hit me and come back as hot water. So that's something they probably already knew, right? Well, yeah, we know this is a problem, but it helps kind of quantify the story and puts value on it to say, it's costly in this way. So wrapping up, again, you can get from kind of this optimization, formulating your problem in this way, you can get insights on management decisions, how they interact, what the trade-offs are, and really see that timing does matter, and you can benefit and affect stream temperatures if you can think about how your different sources have different characteristics in terms of temperature and flow, and if you can manage those appropriately. Of course, out of the kind of engineering, problem-solving realm, there's all kinds of things that make that difficult, but first you have to understand how the system works, and so optimization can help you do that. You may be thinking, but didn't she talk about groundwater, surface water interaction, and if you pump groundwater here, might that have an effect on the stream flow also? Yeah, so that would be an important thing to add to this, right? I didn't talk at all about, yeah, I can pump this groundwater, put it in the river, but what's the timing and effect on stream flow of pumping water from that well? That's a really important question that would need to be better understood to take this anywhere else. So, caveat there. There's always more to do. So with that, lots of fun work. There's folks at the Watershed Sciences Center at Davis that are continuing work in different ways. I want to acknowledge the Nature Conservancy who funded quite a bit of this work. And they are landowners up there and provided access to their land and some of the portions of these creeks and streams too. So with that, any questions?
All right.